and then Church's thesis is that anything that you can do, any computational system that you set up and you can implement, the Turing machine can do, and conversely. You can mimic a Turing machine, just walk through the state diagram, et cetera, and a Turing machine can mimic you. This we haven't actually made concrete, but no one seriously doubts that now, and it all comes down to the finite distinguishability of symbols and states of the machine, memory, your brain. Okay, let's prove that the distribution on a Markov chain show d mu n prime is decreasing for Markov. Well, let me define what those are. Mu n is the distribution on the states x. Then we have a p of the next state given x. And that gives you, so we're state x, we go to state y, and there's a certain distribution, mu n plus 1, on distribution on this. So we have a Markov chain. This is P of j given I, and this is mu of I. And mu equals mu P. That is, if it's a stationary distribution, it's unchanged after one step of the Markov chain. Now, what I was interested in is what if we start with a non-equilibrium distribution, thus I put a n on it. At time n, that's the distribution on the state space of the Markov chain. So I'll start in mu n prime of x, but I go through the same transition, p of y given x, and I now have a y, and now I have a mu sub n plus 1 prime on the state space. Now, I know that if I put in, we recall, if I put mu in here, then I get mu out. That's what the stationary distribution means. There. It's unchanged after one iteration of the process, and therefore after any number of iterations of the process. Okay? Here's a nice way to look at the set of all probability distributions, non-negative summing to 1. Here they are. It's this. It's mu is in the positive order, and the sum of the mu's is 1. So it says, so I'll just pull this out and make it look like this. And for any Markov chain, there's some stationary distribution, mu. But let's look at mu sub n and mu sub n prime. Here are two different distributions on the state space. And now I'm going to move to the next state according to P of y given x. The same P of y given x for each. Well, what this theorem, when we show it, will be true, is that this distance, as you go to mu n plus 1, and mu n plus 1 prime, is this distance becomes less here. Now I said distance, wrong. dpq is not a metric. It's non-negative. It's equal to 0 if and only if p equals q. That's good. That makes it a metric so far. But it doesn't satisfy the triangle inequality, and it's not symmetric. Nonetheless, it has so many properties, we'll just loosely call it a distance here. So I want to prove two things. One is that distributions get closer in relative entropy as time goes on. And I'd like to show that they get closer to the stationary as time goes on. In fact, we know from other considerations by taking the second eigenvalue of P that the convergence is exponentially fast. But that's another story. Here we're just interested in monotonicity. All right. Recall chain rule. D P of xy, Q of xy. These are both joint probability mass functions, non-negative, summing to 1 on x cross y. Is d of p of x, q of x, plus d p of y given x, q of y given x. Where these are appropriately defined, and we have defined them before, and it's in the text. So in short, the distance between two joint distributions is the distance between the marginals plus the distance between the conditionals. Now, let P of xy be mu sub n of x times P of y given x, and Q of xy, so let this P2 be mu sub n prime, some other distribution on the initial state x, but the same transition, P of y given x. All right? Now, the distance between P and Q fractures this way, so this becomes d mu n prime, the distance between the marginals at time n, plus this distance. But P of y given x and Q of y given x are the same. P of y given x and Q of y given x is P of y given x, so the distance between them is 0. Again, algebraically it just follows. Now, but I'm going to expand this the other way. D P of y, Q of y, plus D P of x given y, Q of x given y. So that's, again, a legitimate, we're just expanding it with the other variable first. But this is precisely the distance between the mu's one step in the future. This is d mu n plus 1. Mu n plus 1 prime. The distance between these two distributions plus d p of, and now I'll put in the arguments, although this is just a functional of the distributions, but these will remind us what they are. P of x sub n given x sub n plus 1 times q of xn given xn plus 1. But this is a relative entropy distance, so it's greater than or equal to 0. So now we have that this quantity is equal to this quantity plus something greater than or equal to 0. So therefore this is greater than that. Thus, d of mu n plus 1, mu n prime, greater than or equal d of mu n plus 1, mu n plus 1 prime. And that's what we desired to show there. So for a Markov process, the relative entropy distance between your distributions gets smaller and smaller and smaller. Now, as a special application, let mu n prime equals mu. Thus, mu n plus 1 prime equals mu, the stationary distribution, because mu equals mu p. And therefore we have the conclusion that d of mu n, the distance between your non-equilibrium distribution at time n and the stationary is decreasing. And it's decreasing to 0, which we haven't proved, that the limit is 0, because for that we would need irreducibility of the state transition matrix P. But with that, you could show that the limit is 0. And that's done in the original work of Kuhlbeck in his book on information theory and statistics, so that the limit is actually 0. So this is really nice. It says that say mu is a stationary distribution, that mu n approaches mu monotonically in relative entropy distance. By the way, when distances decrease under the mapping P, we call that a contraction map. And lots of things are true of contraction maps. There's a fixed point theorem. By the way, mu is the fixed point. And a number of things. Again, since this isn't a metric, we can't call it a contraction map, but you can, it acts like one. Yes?
Would it be the fact that our Markov chain only had one station share it with you.